All right, welcome everybody. This is Fred Schenkelberg, and welcome to a short discussion on measurement system analysis. And it's part of the Accendo Reliability webinar series. It's also a podcast. We take the audio and stream it into a podcast feed. So you can find that at reliability.fm, along with a whole slew of other podcasts, both in the product development reliability side and in maintenance world also. So there's a number of different shows hosted there and provided to you there. So I'm sure you'll find something there. Also, I did hit record this time, so I'll have the recording up in a couple of days up on Accendo Reliability under webinars and recorded events and stuff like that. There's a ton of sessions there. I think I've been doing this now for about 4 years, so there's all kinds of topics and all kinds of webinars, and I'm working along with a couple of colleagues on trying to organize the material rather than by media, which is like articles and podcasts and webinars and so on, is organize it more by topic. So FMEAs and oil analysis and reliability planning, testing, so on. So look for changes coming to the site over the next couple of months. And if you have any ideas or anything that you see on the site that you'd like improved or changed or not changed, please let me know. I'd love to hear from you on that as we get into that. All right. So today is on measurements and measurement system analysis. And I catch myself saying every now and then to folks that, the best way to make a statistician happy is to give them a pile of data. And while I do love diving into a Weibull plot or doing some interesting graphics or even the 3D exploration type stuff of multiple variables or doing a complex regression analysis, it all has to have some purpose. We use the data to do things, right? And primarily we're making decisions, and we'll dive into that a little bit more. But the idea of collecting data, of accumulating information is so that we or somebody else can learn something and or more importantly make a decision. Do we need to do something, or do we make a choice of which direction to go to, and so on. And so and Mark, thanks for double checking on the recording. Yep, I did get the recording. I got my little red light going, so I believe I'm good. If not, well, I'll do what I do in the past and just re-record it. So anyway, back to decisions. I think we're in good shape there. But keep in mind that data analysis and the collection of data is not just to fill up your hard drive. Right? I've been into organizations that have terabytes of information that they're collecting, or not information, data that they're collecting. And I asked them what they do with it, and they kind of looked at me like, well, we collect it. Like that was the goal in and of itself. And so I'm like, no, we need to think about this a little more. Now, the hard part of all of this is that the data that we collect are based on measurements. Right? We're measuring the location of something, the clarity of something, or the length of something, or whatever is the account of something, and so on. And the hard part here is that when we're measuring, say, the length of something, it has a finite actual length, right? It has a fixed number out to as many decimal points as you want, actual dimension. The trouble is we don't know what that is. And so we get out a ruler or a caliper or a tape measure or a laser rangefinder or all kinds of different tools and gadgets, and we estimate what that length is. And it really is only an estimate. We really don't know what the actual length of something is when we're measuring length, even after we make that measurement. Now we can use a range of different tools and activities and so on to get a fairly close estimate of that length. yet we will never know the actual length. And there's all kinds of reasons for that. One of them is which tool we're using, what technology we're using. Does the dimensions that we're trying to measure, do they change under the effects of being measured, and so on. But more importantly is the one that many of us know about and have to deal with is measurement error. And the systems that we're using to make a measurement have a lot of variability in them. And we need to understand that variability and know when that error term is acceptable. And we'll dive more into that. All right, so the underlying thing for doing MSA, or measurement system analysis, is to understand whether our measurements are useful or not. Now, some years ago, when I first really ran into the importance of the gauges and measurement systems we're using, was that I was called into, I was a manufacturing engineer in a factory, and we were making heating cables. And the quality department every morning would have a set of products that were manufactured the day before, and they were in a temperature controlled room, and they would go measure the resistance of these products. And if they were within a specific range, the specification for that length of material, they would get a green sticker, and if they weren't, they would get a red sticker. And there wasn't any rework or anything we could do about it. Those were generally then scrapped. Well, make a long story short, one of the probes used to make this reading was swapped out, and it had a very high rate of yield failures. And it really was a markedly difference from one gauge to the other gauge. And typically they were used on one side of the room versus the other side of the room during their measurement system. So I got asked after a couple of weeks of this to go figure out what was going on. Why was this a problem? And was it the room? Was it the types of products stored on one side versus the other? Was it something wrong with our manufacturing process? Was it, why are we scrapping so much more now this month than last month? And what turned out was that when they swapped the probe, the actual device hooking up to our product, with little clamps essentially, they switched it from a 4-point probe to a 2-point probe. And what that means is that the 4-point probe eliminates contact resistance from the probe itself touching the product. And so there's always a contact resistance, and so a 4-point probe accounts for that and eliminates it from the measurement. The other one had a contact measurement, and so some operators would clamp metal to metal very hard, and they would get very little contact resistance, while others put it on very quickly and lightly and would have a lot of contact resistance. And that error, that difference in process from one person to the next, and not accounting for the contact resistance, meant that products were not arbitrarily, but were sometimes viewed as in spec or out of spec when they really weren't. And so it was both creating more scrap, and it was saying good product, something was good when it wasn't. So it was a bigger problem. Well, we quickly changed the probe, and things went back to normal in our typical system. Yet it was one of those very subtle little lessons in my career that said, the measurement system itself is making a huge difference. And sometimes our measurements are useful, and other times they're not so useful. They might just be writing random numbers to us. And that can be bad for us and for our customers. Right? So we use measurements all the time, right? And no pun intended on that. I know I'm using a lot of clocks and timepieces as my imagery today. But we use measurements to make comparisons, whether we're running an experiment, or is this good or not, or is this meeting requirements, is this, like in the quality department, assessing the final test on the products to see whether it meets requirements or not. But we also use measurements on our systems and machines and gauges. In your car, you may glance at your fuel gauge to see if you can pass that last gas station before heading over the hill, for example. Or looking at your speedometer and going, am I within the safe range of speed for this particular area of road, right? Am I driving commensurate with the traffic laws and traffic patterns. We make those kinds of decisions based on measurements all the time, right? Now, some measurements, say with a vehicle example, when you go to the gas station and fill up, and I know there's a couple people from the Netherlands, so I might have to say the petrol station, if that's more appropriate. Or now with electric vehicles, there's usually a gauge involved with, well, how much fuel are you receiving? How much energy are you receiving? And then, especially if you're being charged for it, it needs to be a tracked or monitored or protected type system so that you trust it, that when it says it gives you a gallon, that you're actually paying for a gallon, and so on. Some things don't really matter all that much, right? But when money or transactions or contracts are involved, then the way we make those comparisons, make those measurements, start to really add up in their importance. I know I used to work at a company that was notoriously late starting any meeting that ever occurred. And so people just got used to the idea that, well, if the meeting's supposed to start at 7 o'clock, well, I've got 10 minutes. I don't really need to show up until then. Because if you do show up on time, you're sitting alone for 10, 15 minutes a lot of times. So it was, we're constantly making comparisons, using our gauges and measures to say, is this better than this? Is this correct or not? Are we on time or not? And so on. Now, we also use gauges and measurements in process control, right? In that same factory I worked at with the heating cables, we started to implement process control in monitoring all kinds of different things, and then narrowed it down to the critical ones that really needed improvement. But the first step was always check the gauge. Because if the measurement tool we're using has a lot of error in it, especially if it's not stable itself, we'll believe we don't have a stable process, that we have all these out of control signals, when they're really just manifestations of a measurement error. And so we wanted to make sure that the way we were making measurements wasn't going to mislead us and have us responding to things that really were not worth responding to at all. So the first step in process control, when we're looking for ways to control a process or make it stable and make it consistent and so on, and tighten up its variability, is to get rid of the variability due to the measurement system. Now, you can imagine that the variability of a safety valve and the gauge that it uses to say, yep, it's too much pressure, let's release it now, there's going to be variability there. Yet, if it's too much, you may run into releases when it really is in a safe condition, or not releasing when it really should, and then you have a rupture or an explosion of a pressure vessel, which is usually not a good thing. But we make all kinds of measurements in ongoing ways to, one, make comparisons to how it was doing earlier, but also just to see what's changing, what's varying, what's fluctuating, and is it considered common cause, normal stuff, or is it something that we need to pay attention to, either for improvement or for locking in improvements or making changes to make improvements. But there's all kinds of ways that we monitor things just for that variability aspect. And then finally, we make all these measurements so that we can inform decisions. Right? We're doing experiments, or we're making comparisons, or we're making doing a control chart, making series of measurements, so that we can decide whether the process is good or not, whether this is on time or not. Is there an appropriate amount of risk involved here? Is the variability consistent with what it should be or what it has been, or is it doing something different or strange today and we need to deal with it? When we're measuring reliability activities, we often are are looking for, is it reliable enough? Is it robust enough? Is it going to survive in these XYZ different environments and so on? But those are all into decisions, into are we on par or on course to meet our goals, or are we going to have to make some make some changes and do something different than what we've expected to be doing? But we use information to make big and small decisions every single day. And so when we collect data, it's usually, or I shouldn't say usually because I've seen so many counterexamples, is it really should be aimed at being converted into information for decision making. And if it doesn't have a clear path to that, well, then you don't need to go figure out if it's a clean or good measurement or not, because nobody's going to use it. Yet, if it is going to be used, then the criteria for how good, and we'll define good here in a few minutes, is for of the data, how much measurement error is included in your data, can scale depending on how important the decision is. And that just makes common sense. So I've been talking long enough here. Let me grab a drink of water. So how do you use measurements? I know I've kind of gone over a few that came to mind for me. All right, so Nelson, I see, well, I'm using the audio. Hopefully you've got your audio going now. Looks like the others are getting it. So reporting, yeah, we make measurements to say what's our yield, what's our throughput, what's our, what's the robustness or hardness of something. Good, thanks, Nelson. Let me know. Yeah, Rohit, process control. Yeah, and there's so many applications of that. I think the very first gauge I ever got to play with was a thermocouple. I was checking the settings on a thermal chamber because it was saying 300 degrees Celsius or 300 degrees Fahrenheit, I think it was. Either way, it's pretty hot. But when I put thermocouples in it, I was getting 212 degrees, or in a different location, 280 degrees. So the thermocouple itself was creating about a 50% of the change in the actual value. I was getting mostly lower values than what it really should have been reading. Yeah, cooking, excellent, Carl. Yeah, using the oven or the stovetop. I'm constantly checking the gauge on my grill nowadays to see what kind of heat I'm putting into, especially when I'm not searing something, but when I'm roasting something, I use the gauge there. Yeah, the greenhouse, excellent. Yeah, right now my greenhouse is a bit too hot, so I keep everything out of there. So it goes. Yeah, we use measurements in our personal lives, in our professional lives, in as many different ways as we can imagine. Now, there are 5 recognized, I don't know if they're recognized or complete or if it's a complete list or not. I'm using let me find a copy of it here. The Measurement System Analysis Reference Manual, and the copy I happen to have is the 4th edition. And it's published by, I want to say, one of the auto industry, AIAG, I believe, and ASTM. And I'm not sure who is the lead on that project, but it went through and describes measurement system analysis in great detail. And we would just scratch the surface of it here today. But there's 5 different ways. And this is a quick quiz for you, right? So what are the 5 ways measurement error is described, I should say? And bias is one of them, right? And I'll define bias here in a moment. Accuracy is actually not one of them, really. Accuracy is a combination of a couple of them. Bias and repeatability, I believe, are the 2 that encompass what we commonly call accuracy. Yeah. So bias, repeatability, consistency between measures, we would call that repeatability. If you're measuring the same thing the same way, reproducibility, right? So if Kevin and William are both making measurements, do you get similar or very consistent responses and answers? So we got reproducibility, repeatability, bias. What else is out there? There's two other ones that are a little less precision. It's a combination of, I think, 3 or 4 of these different errors. Right? It's precision deals with, I'm drawing a complete blank on what makes up precision, but I saw that the other day. Linearity, good, Kevin, that's another one. So there's one more, and I'll let you know here, and it's called stability. Right? Does your measurements drift over time? Does the gauge change its reading just because of time? Yeah, but all kinds of ilities getting involved here. So let's dive into each of the 5, and I'll define them briefly, and hopefully you'll see some patterns here. All right. So bias. Bias is just an offset. Now there's 2 kinds of measurement errors categorically. One of them is called location. It's where the difference between the reference value, which is what we consider a known value, or is a, say, think of a calibration where they have a gold standard, or they have a known value that they say, well, this is 1 inch, or this is 1 meter. And then we're making a measurement on, say, length, and we get this offset. When we measure 1 inch, we always get just a shade less than that. And so there's going to be variability in our measurements of actually measuring the same thing. But on average, that difference between what our reference value is and what our measurement system's average is the bias. Right? And so it's just a shift in the nominal value that we get. And so it's measuring the same thing on the same item. All right, and it may or may not be with the same person and so on. Oftentimes when we test for it, it's the same person, same part, same characteristic. The hard part with bias, in my mind, is that it encompasses not just the manifestation of the measurement system, it also includes the appraiser, the person making the reading. If we want a larger or higher reading, we may interpret our readings, if it's open to interpretation, slightly higher or lower. Think of it as a caliper, and you're reading a graduated scale. Then we are interpolating what's the reading, because it might not line up exactly on a mark that gives us a clean reading. We can, depending on how we look at it, how we, what filters we're using to make the reading, how quickly we do it, we can also, with a caliper is a great example, is we can press a little harder or press a little lower. We could tilt it slightly. A lot of times that's even done unconsciously in order to see a reading that is the reading that we want to see. That is very, very different than what measurement error bias is called. That's just a bias in the way we go about making readings, and that's a whole other topic. It overlaps a bit with this term. The measurement error bias is pretty simply just the gauge itself is a little short or it's a little long, and it's consistent. And if we know what the bias is in the calibration process or in our measurement system and analysis, we can account for that bias and add it back in to our measurements. Now, it's a little more complicated than that, but we can account for it for a particular system that we're using. There's all kinds of causes. From a system needing calibration, types of measurement systems that do need calibration, worn equipment. I had some woodworking tools and gauges that they're just, they're worn, they're slightly bent, which makes it tough to make a straight line measurement, things like that, right? My tape measure, there's a little tongue on the end of the tape measure that if you're hooking it over the end of it, it accounts for that difference versus when you're pushing it flat against something. That little tongue moves in order for your 0 point to be where it should be. The trouble is that little hole that rivet slides in, over time elongates that hole, right? And so I'm getting a bit of bias depending on which measurement I'm making. Either I'm a little bit too long or I'm a little bit too short, because the ability for the tool itself to account for how I'm using it has been worn, has been damaged. Environmental effects. My metal rule, when it's warm, expands, right? When it's cold, it contracts, and so I get different readings. And so all of these different things apply in how we offset or bias our readings. And you're going to see many of these causes over and over again because they affect almost all of our parts of it. Yeah, in operator fatigue, it's part of appraiser error. It can be. You'll see it again when we talk about repeatability and reproducibility, which are more common. Bias almost always is accounted for in the design of the equipment, of the measurement system. Now, of course, equipment that's worn or not cared for or has extreme environmental effects may go beyond that the gauge design's capabilities. So one of the first steps in any measurement system is, are you using the right gauge? Are you measuring it appropriately for what you're looking for? Bias is often part of the design of the equipment, and if it's known and it's a calibrated system, it's often a key part of the calibration is to account for that bias and add an offset. So if you've got equipment that comes back from calibration and it has all these calibration constants applied to it, those are almost always accounting for bias. Now, of course, they can account for other measurement error sources as well. Yeah, now, Carl, I'm looking at your note here on the blood pressure and pulse rates depending on the amount of activity. It definitely occurs, and I know that some measurement systems account for the state of the person trying to read it. That gets into more human factors, but the person, when they're involved in actually making the reading, right, it's not an automated system and it's not completely set up, and it's not left to the designer or installers to make sure the measurements are correct. But when you're reading a caliper, for example, or reading a clock, human part of the system can be pretty significant contributor to measurement error. And I think many of you already know that. Right? I once heard, and I don't know, I couldn't find the reference for it, but I once heard that a manual measurement process, counting on a person to do an inspection, and it was a visual inspection of a product. Like, is this a good, is the typeface on this clock appropriate or not? And just do a visual inspection of it. Is it lined up correctly? Is it clear? Is it whatever criteria you're using for visual inspection? Is that a human can make visual inspections at about a 50% accuracy rate. They can determine what is good versus bad about half the time correctly. And even averaging that doesn't help you a whole lot, because it just is such a horrible way to make a measurement. And there's all kinds of bias that gets involved in that, of course, but it's also that the measurement tool we're using, the person and their visual acuity or their touch or their sound, ability to hear a particular sound, changes dramatically with fatigue or with environmental conditions. And so it's most measurement systems that rely solely on a person to do it are, in my book anyway, suspect. All right. So measuring it is really, you need a good set of references that are masters, that you have a known value as well as we can know it using some other measurement tools. Usually most of our organizations have calibration labs, and then they have traceability back to a national standard of some sort for critical measurements we're making. And so if you have reference material or known materials, and then make repeated measurements and have different people do it, use your tools over different points in time, account for, you can get as elaborate as you want, but it's account for different environmental conditions, time of day, lighting, whatever affects the way you would normally be making these measurements. And that average then gives you a basis to determine your bias for that measurement system. And it can be a quick and simple set of experiments to determine this, or you can get very, very sophisticated with it and determine it a bit better. For critical things, part of the bias measurements are done during calibration. Okay, and I talked a little bit about just the personal bias, the filters people carry with them as they make measurements. And I remember one of my bosses years ago, a manufacturing engineering director, he said, well, keep measuring it until you get an answer that I like. I'm like, okay. So what do you like? I'll just write that down. We'll save us all this time. That wasn't exactly a good measurement system. All right, repeatability. Now, I think most of us on the call and most of us in our careers have heard of gauge R&R, and that's the ability to measure the repeatability and reproducibility of our system. And this is just one half of that. Repeatability is keep everything as consistent as you can. Same person, same instrument, same sample, same part characteristic of that sample. We're measuring the exact same thing. So if I have a little cylinder, I'm measuring the length. I'm not measuring the length one time and then the diameter the next time. I'm measuring the length over and over again. Just me, just my caliper, and I make that measurement and I record it each time. And what I'm looking for is how consistently can I do that. Now that personal bias comes into play here, which makes testing for repeatability a bit more difficult. Because if I know it's a 1 inch length that I'm measuring, and I put my caliper on it and I'm trying to get it square and make the reading, if I see 1 inch, I'm going to record it because I know that's the right answer, right? If I don't know exactly how long that particular cylinder is, I might have 10 cylinders in front of me and they're all slightly different, but about 1 inch. Then I would, and not knowing which one's the longest one, which one's the shortest one, I will use the measurement like I'm measuring something for the first time. I don't know what it is, so I'm going to measure it. So part of the gauge R&R process is the random sampling, order of presentation of a value or a component or an item to be measured to a person so that they don't know what it was the previous time. They don't have that filter saying, oh, this is the 1.16 length item, and so I should see something about that. And then it's one of those where if I know what I'm looking for, it's easier to see. And that's a hard part of making these measurements. So repeatability is same persons, same system, everything as much as we possibly can kept consistent. Do I get the same answer, right? And that is sometimes called the inherent variability of the gauge, right? Is when we're trying to keep everything constant, how good is the gauge itself? And so the measurement system we're making. And so that's repeatability. The problems are that the causes of repeatability is that the sample itself varies, right? That little metal cylinder may change its length depending on the temperature in the room. Now, if my gauge is sensitive enough to measure that elongation due to temperature, even if it's very subtle temperature, I would take the exact same sample and I would get different readings. So sometimes it's the sample itself is changing. Now, other times our instrument is changing. Now, that using a caliper, for example, it's made out of metal, and it may be responding to temperature. Now, oftentimes the handheld little calipers that I've made dimensional measurements with are not precise enough to measure its own elongation and so on. Right? They're not made out of materials that have huge coefficient of thermal expansion. They're chosen and designed not to use those kinds of materials. Yet they do change, right? And so if I'm looking at the gauge and it's a graduated, and it's closer to the 8, but not quite to the 8.5, the subtle variations may make a difference as to what my final reading would be. Technique. Calipers are the greatest ones to prove out how important gauge R&R is, because different people use those measurement tools in different ways. They know to find a flat spot, or they know to not over compress it, the dial, and so on. Just the way you handle a gauge can make a huge difference to it. The tool itself can vary. Every time a surface mates to another surface, it changes. There's some transfer of atoms and molecules. There's an accumulation of debris, or the knocking off of debris at a very, very small level. But over time, that can add up and become part of the gauge's source of variability. The hard part with repeatability, especially with people involved, is that we're probably the bigger source, at least in my experience. So the advent of jigs and measurement containers and predisposing things to certain temperatures or conditions helps us to minimize many of these different variables that affect the resulting measurements. Right? For testing for repeatability, it's, as I mentioned earlier, it's part of what we commonly call a gauge R&R, but it's essentially just having somebody make the same measurement over and over again. So it's part of a gauge R&R where the same person with the same gauge sees a set of items to measure, say 3 times. And so it's just looking for, did I measure item number A the same all 3 times I did it, say spaced out over a day or so of time to make these measurements. And if not, then I get some variability, right? I'm almost guaranteed to get some variability. And so that is a way to measure the amount of repeatability of that gauge or that measurement system. Now, one of the questions is, and I've heard this explained a lot of times, is, well, if you know you've got a lot of measurement error, just make lots of measurements. What's wrong with that concept? Yeah, good one, Ray. I hadn't thought of that. The special cause events are ignored, right? Stacking up of multiple errors. If you have a bias, for example, it's going to be consistently off, right? And so averaging will just get me a better wrong answer, so to speak. Repeatability, right? If the gauge itself has a significant amount of variability in how it actually is able to make that reading, yeah, a little bit of averaging may help us get there to smooth that variability out a little bit. Yeah, you need to know the amount of error that it's contributing to even get close to figuring out how to average it out. And then why not just fix the gauge or improve the process or use a better tool? Yeah, with statistics, we can get to anything we want. We can feel better. Well, we made 10 readings and we averaged it. So, okay, were those 10 higher than expected readings? Or were those 10 lower than expected readings? And so on. With automated systems, we often see this where we know they get variations in, say, a fluid level in a vessel, and we're trying to make that reading. Well, if the fluid surface is agitated, there's waves going around, how do you get the average height then? Well, multiple readings over a cycle that would account for all of the highs and lows of the normal turbulence. Well, now we can run some experiments. We could figure out if that gets us close enough to the reading that we want. In some cases, averaging helps, and it's built right into the measurement system. In other cases, we're just fooling ourselves. So it's when you know what the source of the variability is, and will averaging actually help you get closer to a true value, then it's appropriate. Otherwise, we're just fooling ourselves. With the right maintenance calibration, there's all kinds of systems that are really, really good. And the hard part is, it's by design, right? The team that's building that gauge and installing that gauge and using it knows what they're doing and understands the sources of variability that, in, say, a averaging, can address and handle. The hard part is that when like this one manufacturing boss I had said, well, just keep reading it until you get the reading I want. And I read it 10 times and only one of them passed the criteria. Okay, great, ship it. Well, I don't think that was a useful conversation, right? Or that was actually really making a viable, accurate reading to make a decision. We were just trying to justify somebody's opinion and need to actually ship the product, which wasn't excellent. It didn't work for that person much longer. It was like, no, that's not. Why am I wasting my time making the measurements if you're just going to ship it anyway? Kind of thing. So, all right, reproducibility, the other side of gauge R&R. Now this part is, can Carl and William and Kevin all make the same readings? Right? If we're going to go measure the length of the cylinder, we give you 3 different calipers. You will go off and you make your readings, and we come back and compare the results of the 10 samples that I gave each of you. And if it shows up like this, where A, and I won't name which one's A, is a little bit low every time, right? B and C are closer. We don't know if that's close enough or not. But the difference between people is in our local environment, our local circumstances, our different actual calipers, those all contribute to the measurement error called reproducibility. Now, if we're all using the exact same gauge, we would expect this variability to be a little bit smaller. If we're doing it at exactly the same time in the same environment, we would expect this to be a little bit tighter. Right? If we're really interested in the difference between the appraisers, let's try to keep the environmental and gauge variability to a minimum so we can focus on the method that people use to make the measurement. Right? Setting it up, actually reading the scales, any of the prep or pre-work that needs to be done, all those kinds of elements from start to finish of that process that we're involved with. If you're trying to get it so that it's reproducible between our factory here and the factory down the road and the factory overseas, that we're all using the same reproducible method of making a measurement, well then we're going to be using different environments, different gauges, different systems, yet we still need it to be reproducible good enough. the spread needs to be minimized. And so it often takes training, consistent systems, consistent procedures, those kinds of things, and when important, consistent environments. So the reproducibility is looking at a bit more variability than what the repeatability error is, right? So while that one's the inherent one, this one allows us to transport this measurement system or have it done in different locations and get comparable results. All right, so some of the causes, I shouldn't say problems, but causes of this is, again, the differences I just outlined, right? If we can control everything, then we're doing repeatability. But usually we have a different gauge. There's a gauge in our lab and there's a gauge in our factory's lab. And are they consistent enough to minimize the reproducibility source of measurement error? And of course, environmental and appraiser and operator differences impact this one also. Whereas in repeatability, we try to keep those to one person doing it in the same environment, in the same gauge, and so on. So testing for this is part of Gauge R&R, right? And here what we're doing is we've got different appraisers. So the part of the Gauge R&R where they want 2 or 3 different people making the measurements, or 2 or 3 different gauges making the measurements, is then we're looking for the reproducibility, and at the same time, we're also measuring repeatability so we can separate out the within variation of the gauge itself out of the error that's being contributed by different people, different gauges, and so on. And so that's why it's often done together, Gauge R&R, because they're really measured pretty much exactly the same way, but we're looking for the within and between sources of error. And I'm not going to go into Gauge R&R in any great detail. I'm pretty sure I did a webinar on that, and if not, there's plenty of online material of how to go about doing that for all kinds of different systems. So let's say I make a measurement here, and I measure this glass to be 6 inches tall, right? And if somebody, and I know we had some folks from Europe, if you're measuring it and you get that it's, what would that be, 3 centimeters tall, or would it be more centimeters? I have no idea. If I can't translate it, I guess I don't have a really good reproducible system, and apparently years ago there was a crash on Mars because of that. But the idea is if I measure it and I say this product is meet spec and it's good, and our customer support center somewhere in Europe says, well, we measured it and it shows that it's bad. Is it because of the 2 locations? Was it because of the transportation from one location to the other? Or was it the difference in our gauges? Was it the difference in our measurement systems? So if it's not reproducible, that error can lead to conversations and discussions and hand-wringing and back and forth over what is, we hope, to be a measurement error that we can deal with. We can uncover and resolve and improve our measurement systems. So that when we say this is in spec, when I measure it somewhere else, it is clearly the same. It's either in spec or it's not. And that underlies that decision piece that all of these measurements have to deal with. Okay, so stability. This one is really dealing with time, right? Does your measurement drift over time? And so this one is more difficult to measure because what duration of time matters, right? Now, some measurement systems are only really stable for a few hours and then they need to be calibrated again. I know I worked with a medical device measuring white blood cells, and it had to be calibrated every day and reset. And for if it was turned off for, I think it was like 2 hours, then it had to be recalibrated again, and so on. So its stability, and because of the importance of the measurement, it was a diagnostic piece of equipment, the stability had to be consistently reset and rechecked. And then the amount of correction over time was tracked, like in a control chart, essentially. And once it got out of control, then it went back to a rebuild and a more extensive recalibration and alignment, essentially, to use an analogy. But the characteristic is the same characteristic, same part, but over time. And so what I'm looking for is, does my rulers down in my workshop, are they warping or are they shrinking? If it's a wooden ruler, is it drying out and actually changing its dimensions over time, and so on. Again, well, I should mention that the stability is the third of the location errors, right? It's an offset like bias and like repeatability and reproducibility. It's a offset from the true value to what we're measuring, right? So the problems with it is that the causes can be aging or drying or fatigue or seasonal environmental effects. I ran into that one a few times. In the winter, we got more product showed up low in our specification at the end of the season, or in the summer, it was always in the high end of our specification. And it turned out to be not the product manufacturing itself. It turned out to be the gauges that had this seasonal response to the environment. And so we started putting in essentially calibration constants to account for the seasonal effects. Now, testing for it is essentially just do the gauge R&R types of measurements over time, over different periods of time. And one of the keys to that is if your appraiser error or contributed parts of the error is consistent, then the remainder of it goes back to the gauge itself, the measurement system itself. The hard part for me is, well, over what duration does it need to be stable? Now, if it's something that is not able to be calculated, like a metal rule, well, then it's a matter of, if it becomes unstable at some point, then it has to be replaced or retired and replaced. If it's something that can be calibrated, then it's a matter of, well, setting your calibration sequence in order to bring it back into alignment with where it should be versus it's drifting off from where it should be given us. Now, the hard part here, one of the considerations is, well, how do you tell if it's my manufacturing process or is it my gauge that's unstable, right? If I'm doing a control chart and I'm looking for signals of instability or out of control signals, is it my gauge or is it the process? And so paying attention to the actual measurements as they're being made is a critical factor in this. If we know that we just changed batches of material, raw materials, and then we started getting out of control signals, well, it's likely we can do some experiments to determine what changed in that materials with using different gauges. Or if that's not the effect, well, it's a worthwhile question to ask. Is my gauge correct or not? So can I verify it? Can I run a quick test to make sure that this measurement system is accurate or not? It's too easy to trust the gauge. And all too often, though, the gauges themselves are complex enough that there's plenty of ways that they become unstable. Okay, I think this is the last one. Linearity. And this one's almost always taken care of in the design of a product, but it's something to keep in mind as you select what measurement system to use for what you're trying to measure. And so what this is that, let's say I'm measuring the length of something, and I used this 1-inch cylinder earlier, and I mentioned a 6-inch tall glass. If I'm using a caliper that's really, really good in and around a centimeter or an inch, then extending that all the way out to 6 inches may be at the very edge of a handheld caliper's span of what it could actually measure. But getting it level and consistent and parallel over a longer distance may be more difficult to do. So there's a bit of operator error there, but also the gauge itself may not be able to hold the bar that is spanning that distance may not hold its trueness over a longer distance than a short distance. And I'm making this example up on the cuff, but it's part of the design of the gauge. In some areas, it actually makes a pretty accurate reading. In other areas, it's off. And it's just inherent in the technology of the gauge. If you ever used a multimeter, you get to select what band or range of, say, resistance that you're measuring. Are you measuring milliohms or are you measuring tens of ohms, right? But within each of those settings, there's low in that scale and high in the scale. And what we're looking for is the bias consistent. Ideally, there's no bias, but is the bias consistent over that range of those measurements? So if I'm measuring a 10 ohm resistor and a 100 ohm resistor and a 1,000 ohm resistor, is the bias consistent? Or do I get a negative bias or a positive bias at different places, or is it nonlinear, and so on? And so to make these measurements, you need a range of values that are known values, masters or calibration type things, and measure it over the entire range of our system. So again, like measuring bias, but over the spectrum of values we expect to be making readings with this particular device. Ideally, linearity is consistent, and then it's just the bias, and we can account for that. If it's not consistent, is it stable, right? Is the nonlinearity or the offset, the bias change in a predictable way, and then we can account for that. If not, then we've got a stability problem or a repeatability problem in something we're going to need to take up. But you notice in all 5 of these, it's calibration, fatigue, environmental effects, and so on. So there's many, many different causes for these different sources or types of measurement errors that we may run into. Okay, mentioned that already. So final question for you is, how good's good enough? How good is good enough? And you may have heard of the rule of 10, right? If you're going to measure an inch, you should be able to measure to 1/10 of an inch on the gauge. And the calibration should be to 1/100 of an inch in order to measure that gauge's ability to measure 1/10 of an inch, and so on. So it's a generic guideline that's used. Now, if I'm measuring a table to see if it'll fit through a door, I might just put my hands up next to the table and walk over to the door and can I get through, right? It's a pretty crude measurement system, but it might be good enough, right? But if it's close, if I'm within a few millimeters of clearing that door and I really, really need to get this through that space, I might go get a tape measure, or I may take the door, off and open up the frame so that I get a little bit more margin, just in case. It's a little bit more work to do that. So depending on the decision, good enough in one circumstance may be not good enough in another. And I think that's the final thought there. Yeah, the number one thing is, and I'm going to go with what you're saying, William, is make sure that the gauge that you're using is appropriate for the decision you need to make, right? If it's a rough screen to see if it's worth using moving forward and there's not a lot of consequence, go for it. If it's a $100,000 batch of material and you're doing sampling, And the results of that sampling is pass, fail, and fail is scrap, and then you have to pay, you pay for that scrap. Well, you probably want to invest in a good measurement system to make sure that that decision is clean, that good batches are passed through and bad samples are scrapped, and not vice versa. So always look through to what's the consequence in the magnitude of that decision that these measurements are going to be used for. If nobody's ever going to look at it, well, then stop making that measurement. Don't worry about it. If it's critical to your business decisions or customers' satisfaction with your product, well, then it's probably worth looking into what exactly is the measurement error and how can you make improvements. And a big part of that is picking the appropriate gauge right from the start. So we gather data. Let's see, I didn't even update these from the last time, but we gather data and we use measurements to do that. And those measurements help us to gather information in order to make decisions. If the source, the starting point of that, those measurements are adding a bit of variability, the measurement error to it, it clouds our ability to interpret it correctly. And so we may call good products bad and vice versa. We want good information, which starts with good measurements. So.